Hello, this will be a demonstration of Proposition 1 from Book 5 of Euclid's Elements, which says that if there be any number of magnitudes which are equal multiples of an equal number of other magnitudes, then the multiple that 1 is of 1 will be the same multiple that all is of all. What this is going to look like is we're going to be given two magnitudes or any number of magnitudes, but in this case we're going to be given a 2. It's the simplest non-trivial case. So we're given two magnitudes E and F, and we are also given equal multiples of them. So we'll have AB, which is the same multiple of E that CD is of F. That's what it means for one magnitude to be an equal multiple of another, right? So whatever multiple AB is of E will be the same multiple that CD is of F. And what we set out to prove is that whatever multiple AB is of E, right, because it is a multiple, whatever multiple AB is of E will be the same multiple that all is of all. In this case, that AB plus CD is of E plus F. We begin by dividing AB into magnitudes equal to E. In this case, we're going to divide AB into just two magnitudes equal to E, although you can reasonably do this with like if AB equals 3E or 4E, but Euclid likes to work with the simplest non-trivial case, so he'll often work with 2s and 3s when it comes to multiples and multitudes. So we're going to divide AB into parts equal to E, and we're going to divide it into 2, so we'll have AG and GB being magnitudes equal to E, and likewise we're going to divide CD into parts equal to F, so we're going to have CH and HD equal to F, so that AB is equal to 2E, it is double E, and likewise CD is equal to 2F, it is double F. And this makes sense. We were given that AB and CD are equal multiples of E and F respectively, so it makes sense that AB is double E and CD is also double of F. So now, knowing that AG is equal to E and CH is equal to F, right, we made AG and CH such that they are equal to E and F respectively. If we add these two together, then we're going to have equals, right? That's common notion 2. So AG plus CH is going to be equal to E plus F. That's pretty straightforward. And similarly, because GB is equal to E and HD is equal to F, GB plus HD is also equal to E plus F. So now knowing that AG plus CH is equal to E plus F, and so too AG plus HD is equal to E plus F, then we can add these two together again to get even more equals. Again, another use of common notion 2. So AG plus GB plus CH plus HD is going to be equal to E plus F plus F. In other words, AG plus GB, which is AB, and CH plus HD, which is equal to HD, and E plus F simply being double E plus F. We will note that AB plus CD is equal to double E plus F. It is equal to 2E plus F. And we notice that this 2 here is the same 2 that we have up here. So that the multiple that AB is of E, namely 2, is the same multiple that AB plus CD is of E plus F, namely 2. And this being what we set out to prove, we are done with the proposition, therefore, etc., Q, E, D. Now, these propositions in Book 5 are quite difficult to understand, at least with the language that is presented in the translation, right? But we would probably understand these truths more readily if we put them into if we put them into algebraic terms, right? A lot of us have done algebra before doing Euclid, so we're more used to algebraic terms. So what this is going to look like is we're going to have just two magnitudes. We're going to call these two magnitudes just A and B. And we're going to have equal multiples of them. So what that's going to look like is M times A and M times B, right? So MA and MB are equal multiples of A and B, right? Because we multiply them by the same thing. And so what we just proved is that if we do MA plus MB, what we're going to end up with is M times A plus B, right? So the multiple that MA is of A, for example, is the same multiple that M times A plus B is of A plus B, namely just M. And we will probably just recognize this as the distributive property, right? MA plus MB is equal to M times A plus B. And this is how we might understand proposition 5.1 nowadays. So I encourage you to put these propositions in book 5 into terms you might understand more readily, more algebraic terms. Not because the algebraic terms are inherently better than the Euclidean terms, but simply because they might be more accessible, right? They might not be more knowable in themselves, but they might be more knowable to you. They might be more relatively knowable. So I think that is certainly a benefit. Other than that, I have nothing to say about this proposition, so I'm going to simply move on to proposition 5.2.